everyone. This is Heather Archambault. I'm a program manager in the NOAA Climate Program Office, the Modeling Analysis, Predictions, and Projections Program. And I want to welcome you to this month's MAP webinar on seasonal prediction of high water levels, state of the science, and future opportunities. This is part of our long-running webinar series. And I want to thank my colleague Dan Barry for his help in planning this webinar. And so today we have four very distinguished researchers, three from NOAA and one from the Australian Bureau of Meteorology. The webinar presentations will begin with looking at potential sources for ocean predictability, looking at the influence of coastal water levels in the Atlantic meridional overturning circulation, and then we're going to move on and look at current and developing capabilities for predicting sea level anomalies for the Pacific Island regions and U.S. coastal communities. And without further ado, I'll start off by introducing our first speaker, Arun Kumar. He's at the Climate Prediction Center. He's currently the chief of the Operational Monitoring Branch in CPC, and that's within the National Centers for Environmental Prediction. Arun joined NCEP in 1990 as part of the Coupled Model Project, which was responsible for the development of a dynamical prediction system for seasonal outlooks. Arun received his PhD in 1990 from Florida State. His professional interests are quite broad, and they include seasonal climate predictions and understanding of seasonal and decadal climate variability, the global influence of El Nino slip and oscillation variability, tropical air-sea interactions, the tropical Pacific Ocean observing system, and the analysis of oceanic and atmospheric interannual variability in a couple of general circulation models. So now I will turn it over to Arun. Arun, are you there?
Yeah, thanks, Heather.
Okay.
If you can handle it.
Yeah, I'm transferring control to you, and you can share your screen whenever you're ready.
Can you see it?
Not yet.
I don't see the button to share my screen at this point.
There should be a green tab.
Okay. Always something happens.
If you're in the quick start, if you are on the first tab there should be a Share My Desktop button.
But before when we did it, there was a blue button saying Share My Desktop. It is not there right now.
Okay, you did it before. Oh, wait. Here, let me try transferring back to me and then going back to you. All right, I'm going to be the presenter now.
I can see it now, and if you can share it with me. It's grayed out right now. Okay, got it.
Now I'm passing it back to you. If this doesn't work, I'll just run it from here because I have your presentation.
Should work now, okay.
Do you see it? Okay, great. Take it away.
Okay. So thanks, Heather, and also to Dan for inviting me here. So this is a very broad presentation on sources of predictability in the oceans, and I think the subsequent presentations will touch upon different time scales in the context of the sea level pressure. So there is oceanic variability which happens on very different time scales. So you can start from the tidal ones on a daily time scale to weekly, on which you get the mesoscale eddies or tropical instability waves. On a longer time scale from seasonal to interannual, there are modes of variability related to El Nino Southern Oscillation and Indian Ocean Dipole in the Indian Ocean, and then longer time scale, for example, in decadal, you have modes of variability in the Pacific called Pacific decadal oscillations, or in the Atlantic related to Atlantic multi-decadal oscillation, and then moving on to even longer time scale, oceanic variability on a centennial time scale related to thermohaline circulations, or the trends related to changes in the external forcings, for example, slow increase in the CO2. So these are the sort of range of variability that exists in the ocean, and the hope is that you can you will be able to predict part of it in terms of sea surface temperature anomalies, which will translate to changes in the sea level pressure anomalies. So the talk is divided into two sections. The first part is basically gives you some introduction about what these modes look like, and the later part touches on what the sources of predictability might be. We'll start from the seasonal to interannual. The most prominent mode of the variability is El Nino Southern Oscillation. Happens in the tropical Eastern Pacific. Has two phases. One is the warm phase, which is shown in the top left. An example of that is shown in the top left. Relates to a warm state of sea surface temperature in the tropical Eastern Pacific. And opposite of that is a colder state of the sea surface temperature in the tropical Pacific, which is shown in the, an example of that shown in the bottom left. And you can quantify these variations by taking an index in the tropical Eastern Pacific, highlighted in this yellow region in the top right diagram called HIMA 3.4. If you just take the sea surface temperature over that region, and plot the observed time series, that looks something like in the bottom right diagram. So there are times when the sea surface temperatures are warm, there are times when they are cold, and there's sort of quasi-periodic oscillations going from the warm state to the cold state back to the warm state. These sea surface temperature anomalies will translate to, or will also translate to changes in the sea level heights, and I think Elaine is going to talk about predictability of those things. So this is ENSO is the most prominent mode of variability on an seasonal to interannual time scale, but that's not the only one. In the Indian Ocean, there's another mode of variability called Indian Ocean Dipole, which is related to a seesaw fluctuations between the Eastern Indian Ocean near the east of Indonesia and the Western Indian Ocean. So if the temperature sea surface temperature goes below on the eastern side, it tends to go above in the western side of the Indian Ocean. So if you just take the area average of the West Indian Ocean and Eastern Indian Ocean, so these are the respective observed time series, going back to somewhere in 1980 to present. And again, just like in the tropical Eastern Pacific, you can see sea surface temperature tend to fluctuate between the positive and negative phases, and this mode of variability is referred to as Indian Ocean Dipole. So these two are the most prominent modes of variability on interannual time scale. There's modes of variability in the ocean which are related to on the decadal time scale, and there are two of those which are most prominent. One is called Pacific Decadal Oscillation, and as the name might indicate, it occurs in the extratropical and tropical Pacific Ocean. So the top panel gives you some examples of the sea surface temperature anomalies in the shading for the positive phase of the Pacific Decadal Oscillations, and on the right panel is the negative phase of the Pacific Decadal Oscillations. So just take the example of the positive phase, you get negative sea surface temperature anomalies in the northern Pacific, and a positive sea surface temperature anomaly in the equatorial Pacific. One can define an index of the PDO, which is shown in the bottom panel, and again, this index fluctuates in the negative phase, which is shown in green, and the positive phase shown in the right. And one of the remarkable or the characteristic feature of this index is that there's a very slow fluctuation. So there are decades or periods of 10, 20 years or 30 years when the index prefers to stay in a negative phase, in a particular phase, and it flips back into an opposite phase, and then it stays in that particular phase for next 20, 30 years, and hence the name related to Pacific Decadal Oscillations. Again, this is most prominent or occurs in the northern extratropical Pacific Ocean, and also some fluctuations in the tropical Pacific Ocean associated with that. Another mode of variability is related to occurs in the Atlantic, and it's referred to as Atlantic multidecadal oscillations. The way it is defined is take the area average over the Atlantic basin, just average the sea surface in the simplest terms, just average the sea surface temperature anomalies over that. And the bottom panel shows the average sea surface temperature anomalies over the Atlantic basin. So again, just like the PDO, the AMO index tends to stay in a particular phase for a long period of time, then goes in the opposite phase. So if you eyeball this time series, you can see the very slow variations in the sea surface temperature over the Atlantic. And again, these will relate to corresponding changes in the sea level heights, which you might hope to predict, and I think Steve is going to talk about that later. Moving on to centennial time scale, and this just gives you an example. So just take the sea surface temperature basin averages and plot the time series. It is shown from 1950 to present. For the global oceans in the very top panel, then the tropical oceans, Northern Pacific and North Atlantic, and you can see these sort of very slow trends indicating that in most of the ocean basins, the sea surface temperature have gone from negative to a positive value, sort of coinciding with the increases in the CO2. So these long-term changes will also lead to some long-term changes in the sea level heights, and superimposed upon these long-term changes would be fluctuations on the variability on other time scales, which you might hope to capture. So these were just describing some modes of variability in the oceans which happen on different time scales. The predictability refers to that what you hope or what chances you have in anticipating these modes of variability if you know their present state. So if you know what the state of the PDO right now is or what the state of ENSO right now is, can you predict its future evolution in coming seasons, years, or decades? And that's what's a very basic definition of predictability is, and predictability is sort of a prerequisite for having some prediction skill or skill in anticipating these oceanic anomalies. There are various sources of predictability. Ocean has very large thermal inertia, so one of the very first source of predictability is the persistence of the sea surface temperature anomaly, the persistence of the ocean anomalies. So if you know the anomalies now, and since ocean has large thermal inertia, it changes on a slow time scale, so you can use that as a prediction of what might be happening in the immediate future. So that's the very basic source of predictability of oceanic anomalies. And on top of that, there are other sources of predictability which add to skill coming from predictability based on the persistence. There are various sources. One is basic ocean dynamics, so propagation of oceanic anomalies related to oceanic waves, gyres, or the Rossby-Kelvin waves in the different ocean basins. There could be also coupled air sea interactions, whereby if you have initial anomalies, it might influence the atmosphere, which in turn influences the ocean back, and these anomalies can grow with time. It typically happens for the ENSO and modes of variability like Indian Ocean Dipole, etc. Another mechanism is the oceanic teleconnections, which are mediated by atmospheric bridge, whereby the ocean is in one oceanic basin. Anomalies in one oceanic basin are connected with the anomalies in other ocean basins. And if you can predict one, you might be able to predict the others. I'll just give you some examples. An example of the persistent time scales in the ocean. So what's done here, you just take the weekly anomaly in the ocean and do an autocorrelation of that with the subsequent anomalies in the sea surface temperature. If you just focus on the top panel here, which is the persistent time scale for the wintertime sea surface temperature anomalies. And what is shown is, so you start with an anomaly, and when the autocorrelation of these anomalies, the number of weeks when the autocorrelation drops below 0.5, so the longer is the this number indicated here indicates the more persistent these anomalies are, or more predictable these are by knowing their initial state. The red colors indicate that if you know the initial anomaly, then it drops to, then you can explain about 25% of variance or anomaly correlation of 0.5 about 20 to 25 weeks later. This gives you a sort of indication where these persistent time scales are higher or lower. So just for the weekly anomalies, most of the persistence in the tropics is in the equatorial eastern Pacific related to ENSO, and in other oceanic basins, the persistent time scales are much smaller. The basic thing is that this gives you an indication on what time scale you can predict or anticipate the anomalies just by knowing what they are at present. So you can use this persistence, develop a forecast method. So you can just take the monthly mean anomaly, use that to see, use that as a prediction for the next month's anomalies, or the 2 months down the 2 months later anomalies, and this is the map of the skill map of what kind of skill you get. So again, just look at the top panels here. These are anomaly correlations. When you take the anomaly of this month, specify that for the SST anomaly for the next month. So this would be the skill of that prediction. So higher the number, better the skill of the prediction is. And this plot looks very similar to the persistence time scale as you might expect. So just knowing the persistence of these anomalies, you can use that as a basis for making or anticipating the oceanic anomalies in the future. I can do that for different time scales. So what's shown here is for monthly. I can do it for yearly anomalies or longer time average anomalies, and see what the persistence of those anomalies is. So going beyond the persistence, then you can use the coupled models or the dynamical models and initialize the ocean and atmosphere, and use that use those methods as a prediction. So what will happen here is now you have some skill because of the persistence, but now because of using a ocean dynamics or using a model which captures the ocean dynamics, which captures the couple ARC interactions, and if you initialize those anomalies, then those things will add to the predictability or the prediction still coming from the persistence alone. So this is based on a NCEP climate forecast system. It's a dynamical seasonal prediction model. What's shown here is the seasonal prediction skill. So you start the forecast sometime in July and look at what the prediction skill for the subsequent season. For example, October, September, October, or going down on the longer time scale what the skill is, and the darker the purple colors are, better is your skill. So again, the skill is better in the tropical Eastern Pacific, in this case related to ENSO, and also it has already been indicated when you looked at the persistence diagram. You can get some measure of how much skill knowing these anomalies or specifying these anomalies add to the skill beyond the persistent time scale. So as shown here is an example of the skill again based on the CFS. The top panel is the left columns are the forecast skill based on the CFS, and the right panel is the forecast based on persistence alone. So if you get difference those two, that will give you some estimate of what the ocean dynamics, and other ocean dynamics, a couple ARC interactions add to the skill beyond the persistence. So naturally, or as you might anticipate, the skill of the prediction skill on the left panel is higher than what's the skill based on the persistence. And again, the darker the colors are, more skillful is the forecast, and if you difference these two maps, will give you some indication of what the other sources of predictability are adding. There are other sources of predictability. For example, there's some oceanic teleconnections. If you have ENSO variability in the tropical Eastern Pacific, it generates some atmospheric circulation. which influences the oceanic anomalies in other ocean basins. So if you can predict them so well, you might be able to predict the oceanic anomalies in other ocean basins. Recently, there have been some attempts to make predictions on the decadal time scales, and I think Steve will give you a broader introduction or overview of those. And what is done here, just like on the seasonal time scale, you initialize the ocean, integrate the model for 10 to 20 year time scale, and try to assess the skill of these kind of predictions on a very long time scale. And as you might anticipate, you might expect the predictability to be in the ocean basins where the modes of variability like PDO and AMO are the most prominent. So what's shown here is the result in terms of assessing the skill of the decadal predictions based on a coupled model. The top panel shows the prediction skill by initializing the coupled models. The left column is the skill based on a 2 to 5 year time scale, and 2 to 5 year time averages from now, and the right panels are the skill for predicting the time averages from 6 to 9 years from now. Again, the redder the colors are, better is the skill. The caveat here, the catch here is that you can get a lot of this skill just by specifying the changes in the external forcings from the reference state you're predicting. So the bottom panel shows the difference in the skill, which is coming from specifying or initializing the ocean states. And if you look at the top left, bottom left panel, so it gives you some indication that the additional skill coming because of initializing the ocean or predicting the ocean dynamics or initial conditions of the ocean state is generating some skill which might be related to Atlantic multidecadal oscillations. So just to summarize, there are modes of oceanic variability which exist on all different time scales, starting from the daily, starting with tides, and going to seasonal to interannual, decadal, and longer time scale. There are various sources of predictability which allow you to anticipate these anomalies. These are persistence, advections, or the movement of the oceanic anomalies because of ocean dynamics, or the amplification of the decadal anomalies because of couple layer C interactions. These sources of predictability allow you to anticipate the future of these anomalies and add to the predictions, or allow you to have some prediction skill. And various methods have demonstrated prediction skills on various time scales, particularly on seasonal. And there's some ongoing attempts on assessing these predictability on decadal and longer time scales. So with that, thank you very much. And if I answer any questions, please go ahead.
Arun, thanks so much. That was great. So now we have time for a few minutes for questions. And to ask a question, if you are remote, you just need to hover your cursor over the green tab that you'll see at the top of the screen and click the Participants button, and then click the Raise Hand logo, and then the hand logo will appear next to your name, and then I can unmute you and you can ask a question. So first, are there any questions for Arun in the room? Okay. Anyone online, would you like to ask a question? Okay, so Ken Mitchell, I unmuted you. You can go ahead with your question. Ken? Okay. Hey, Ken, are you there? Do you have a question? Okay, anyone else?
This is Ken. Can you hear me now?
Okay, yes, I can hear you now. Go ahead.
Sorry about that.
No problem.
Yeah, sorry. Hey, Ron, very interesting. Could you go back a slide or two? The one after that. The second to last one, I think. The one just before, The one just before your conclusions.
Okay.
Yes, this one. In the top row, panels A and B, could you describe those again? This is baseline skill in what sense?
So this is a skill just like you do in the seasonal forecast. You do a decadal forecast, so you initialize the ocean and atmosphere and integrate it forward. So you get the skill in predicting sea surface temperature. For time averages, the left one is 2 to 5 years from now, and the right one is for the 6 to 9 year average of sea surface temperature from now.
What I don't understand is the difference between the top panel and the bottom row, the top row and the bottom.
So the top panel is a skill you get from initializing the ocean, but implicitly it has the effect of increases in the CO2. So if you don't initialize the ocean, if you just take the effect of the CO2, so that's the difference in the skill at the bottom.
Okay, I understand. So, okay, thank you.
So what you're seeing in the bottom panel is, in addition to CO2, what you get by knowing the state of the ocean now.
Okay. How do you initialize the top panel? If it, if it's not actual initial states, how are those runs initialized with this?
No, they are initialized from the observed state of the ocean to the extent you can measure and analyze the ocean, and also the observed state of the atmosphere, but that doesn't matter that much. But so you do take all the ocean observations, do the analysis, and start the forecast from that ocean analysis, just like we do in the seasonal forecast.
Okay, so to obtain the bottom row, you also did runs that you did not initialize, and then you subtracted the two skills?
Right, so bottom runs would start very long time ago. So you lose all the memory because of the ocean. Whatever is left is just the influence of CO2.
Thank you, I understand now. Thank you.
Okay.
Okay, thanks, Ken. And thanks, Arun, very much. And now let's go on to our next speaker, Stephen Griffey.
You're going to take the control back, right?
Yes, I'm going to transfer right now. Yep. Okay, so it's passing presenter privileges to Stephen Griffey, and while he loads up his talk, I'll introduce him. Stephen is a senior scientist at NOAA's Geophysical Fluid Dynamics Laboratory, and he has expertise in ocean physics and numerical modeling. And among a broad range of research activities, he has particular interest in Southern Ocean and Atlantic circulation dynamics, with a special emphasis on how circulation variations impact patterns of regional sea level. Stephen, you can go ahead whenever you're ready.
Okay, am I being heard?
Yep.
Okay, so this is a talk written by a collaborator of mine, Jianjun Yin, who you see here listed as the lead author. He gave it at the Ocean Sciences meeting in New Orleans just a few weeks ago, and I thought it was appropriate for this group. And Paul Goddard is his student who did most of the heavy lifting here, and myself and Xiaoxing Zhang at GFDL helped out a good bit. We're going to focus here on regional sort of events linked to the east coast of the U.S., linked to the AMOC, the Atlantic Meridional Overturning Circulation. So not large-scale patterns necessarily, but connections between large-scale and the coast. And looking in mostly observations here. This is not so much of a modeling talk, although there will be some models brought in. So what you see here is the east coast of the U.S. with different regions, southeast, mid-Atlantic, northeast, with the stars signifying where tide gauges exist. And the right panel, which is a time series going back to the early part of the 20th century of the sea level measured, averaged over those regions. The top of each of the individual panels is a time series for the sea level, and the little boxed, sort of looking like dotted figure is a number of tide gauges. That's important to note how many tide gauges we actually have, and it's one of my pet things that we need more tide gauges. Anyway, what you see is a general rise along each of the sectors, with the mid-Atlantic and the northeast showing more of a rise than the southeast. Some of that rise my understanding is that some of that rise is due to subsidence in land, glacial isostatic adjustment, and some of that is due just to long-term climate change, global warming sort of thing. And the focus of this presentation is one event, and it's just really picking apart, just pulling a piece of hair out of this long time series, a particularly big event that happened in 2009 that is depicted here in the Northeast time series. This here is the time derivative, or just the time difference between two successive years of those tide gauges. And you see in 2009 that there's a 3 sigma event in the Northeast, whereas in the Mid-Atlantic and in the Southeast, there's not that much going on that year. There is a big event in the Southeast in 1949, but we're going to focus on 2009. And you can do some probability and say that that's like a 1 in 850-year event. You know, it's kind of inferential sort of stuff, but it is an extreme event. And so, what's going on is the question. The large-scale context of what's going on there. On the lower left panel, you see the satellite analysis of sea level called AVISO, and it's a satellite product that, or analysis of satellite data, showing that there's separating the Gulf Stream, basically separating Atlantic low in that year, sea level low, and from an Atlantic high during 2010. You see here anomalies relative to the long-term mean. So in 2009, 2010, the extreme sea level event occurred during a short period, actually, of global and regional sea level fall. If you do an average over the Atlantic, you see the lower right panel, and it's actually a regional sea level fall when you average over the whole basin. And over the whole globe, there was a regional blip downward in 2010, 2011. So, but, you know, going back to the previous figure, the coast tide gauges were seeing a rise. So, you know, it's one indication of the difference between global mean and even regional mean from what's happening at the coast, and it's important, you know, coastal impacts and so forth. That's where these events, sea level rise, is going to impact humans. So the connection to the Atlantic meridional overturning circulation is shown in this slide here, where you see the tide gauge in the Northeast in the top left time series, and the bottom left time series is a time series from RAPID. RAPID is it's a time series that spans the Atlantic at 26.5 degrees north. That gives a very important. It's been going on now since the early 2000s, about a decade plus, of the Atlantic transport at that latitude, and it is a really rich data set, and we're hoping to keep it out there for an indefinite time. I mean, hundreds of years we should have monitoring of these transports. And you see a 30% downturn correlated quite closely in time to that extreme event in the Northeast coast. So if you do a correlation, the pattern correlation in the top right panel of the AVISO sea level analysis with the RAPID time series, you see a negative correlation along the coast, which means that when you have a downturn in RAPID, you have an upturn in sea level along the coast. So you just have to switch the signs here. So it's a fairly good correlation as correlations go from geophysical data. And you can see that there is a regional correlation along the coast of a downturn, or negative correlation along the coast, whereas in the open ocean and the Atlantic, there's a more positive correlation. And you can do some linear fits to see, well, if you have a decrease in the Atlantic overturning based on RAPID, how much does that correlate to a sea level rise along the coast of the U.S.? And you can get roughly, 13 to 17 millimeter sea level change correlated with about a sphere drift change of the transport. So again, a sphere drift is a measure of mass transport in the Atlantic, and these these fluctuations, as you can see from the AMOC time series, they go up and down about 5 or 6 sphere drifts on this big 30% downturn, and interannual variability can be on the order of a few sphere drifts as well. So that's the connection that's really intriguing to us, interested in understanding the AMOC from a mechanistic perspective and understanding its potential impact along the coast of the Atlantic region. It's a compelling correlation that it's also represented well. This correlation is reflected well in models, and in fact, it's probably an example where models anticipated observations before we had sufficient observations to verify the models, where the models were showing a very similar pattern, at least on the large scales of this correlation of coastal sea level anti-correlated with the strength of the Atlantic transport, the AMOC transport. So if we could, the inference here is if you could predict the Atlantic fluctuations, you could potentially predict the coastal sea level. So that's the sort of carrot that's sitting out there. And I'm not going to show you anything about predictions because that's still an ongoing quest. I'm just showing you a potential application of Atlantic prediction that could be useful to coastal sea level. So breaking down the fluctuations of sea level a bit more, you can do you can break down sea level fluctuations into what's called steric fluctuations, which are associated with changes in the heat and the salinity, the heat and salt content of the ocean, the density changes, and you can also break down that into mass changes. So what you see in the upper right figure here is the steric component of the sea level change, and it's showing some positive rise in the interior of the Atlantic due to thermosteric effect, warming anomalies, but not much along the coast. Okay, you know, it can provide some changes in sea level, but the question here is what's going on along the coast. And if you now look at this lower right figure, which just came out last year, I would claim that this is an amazing analysis that the people at JPL did, Jet Propulsion Lab, looking at GRACE data. GRACE is a satellite product that measures gravity field of the planet. And it's so well done now that you can measure the changes in the gravity field due to motion of the ocean water, as well as land water and other motions of mass around the planet. And so what Lander et al. Show is a figure here where in the 2009-2010 time scale, they see this loading of mass. Now blue here is positive, so a loading of mass along the coast. Now this is a very coarsely resolved, 300-kilometer square grid that they're having here, because they can't really do much better than that with their data. But this is just an astonishing figure in my mind, because it's exactly what the models are also showing, where you have fluctuations of sea level along the coast that are along the east coast of the U.S. that are very much tied to motions of movement of the mass of the seawater on or off the coastal shelves. And it's less associated with local warming along the coast than it is of motion, namely a steric effect, but instead it's due to a mass effect. So here's another paper that just came out earlier this year from PNAS, looking at, this is kind of, this sort of, what's that video game, sort of Pac-Man looking figures here. Looking at decomposing the sea level changes around the planet due to different effects. And so the one that's dotted, circled here off of the West Pacific, it's attributed largely to changes in steric, namely motion of the heat content in the ocean that's causing sea level rise in the West Pacific. And that, we think, is due to fluctuations in the PDO, which is a pretty major event for these people. A decadal sort of scale of relative sea level rise for the island nations in the West Pacific has been pretty dramatic. Whereas when you go to the northeast U.S., it's more there's a more contribution from what's called OBP, or ocean bottom pressure, plus other. And that's, again, consistent with this figure from Landerer et al., where you see changes along the coast due to some pressure loading or mass loading along the coast of the U.S. And so going down to the lower right panel here, you see in the middle of 2009, 2010, you see an uptick in the bottom pressure along the east coast of the U.S. as a time series from Grace. So thermospheric effects are important as well, and they do contribute to changes in sea level along the east coast of the U.S. I don't want to downplay that completely, and in fact, there has been warming along the east coast of the U.S., in the Gulf of Maine in particular, in a different study that came out from GFDL by Vince Saba and others, other NOAA people as well as people at GFDL, looking at one of our high-resolution climate models showing what you could maybe call as a heat wave in the ocean. And that effect, you know, warm water expands, and no matter what, even if you don't have much pressure loading of mass motion, if you warm the water, you'll expand it. And this result in particular is particularly relevant for fisheries as well, because there's been some real drastic fisheries changes in the Gulf of Maine region associated with some rather large ocean water warming. And for the first time, I think, in a climate model, we've been able to simulate that reasonably well with a high resolution of a 10th degree ocean, which is much bigger than the typical climate models, much finer resolution than the typical climate models are. But I claim that to do impacts of climate fluctuations along the east coast of the U.S., including sea level and temperature changes for fisheries and so forth, you need to have a fairly good resolution model, if not 10 kilometers, if not finer, partly because you need to represent the boundaries very accurately to get these embayments and these channels and so forth represented in your model, and partly because the Gulf Stream representation is so much better when you go to higher resolution. And the Gulf Stream is so tied to what's happening on the east coast of the U.S., because the Gulf Stream is a component of the AMOC. It's the one that brings water northward. And then there's a deep western boundary current that brings water back southward. And both of those features in our simulations are just dramatically improved with higher resolution. It's not to say they're perfect, but they are just better represented, and part of it is just they're there, as opposed to in the Gulf of Maine and the Northeast Channel or something like that. It's a feature off the Gulf of Maine. It's just completely missing. Even at a 25-kilometer model, it's hard to get that feature. So the NAO, that's also part of the title and part of the story. The NAO, of course, is a very big, has a big role in all of Atlantic variability. It's the changes in the winds affect the transport of the Atlantic circulation, and the Atlantic circulation, we think, might also play a role in fact impacting the NAO. It's part of the ongoing debate / research into Atlantic variability. There is no grand unified theory yet for all of what I'm talking about. There's just lots of interesting ideas, and models are different. The models behave differently. So in the 2009-2010 era, there was a big negative NAO, as you can see in the time series in the top right here. And that produced some winds that are shown in the lower right based on a reanalysis from GFDL. And you can see that the winds were blowing in a counterclockwise, anomalously counterclockwise fashion. And so producing potentially some Ekman transport toward the coast. And additionally, there's an inverse barometer effect, that when you have a low pressure from the atmosphere sitting over the ocean, you will let the ocean rise. It happens all the time in hurricanes, for example. It's a big effect of hurricanes and sea level. It's just the fact that you have less pressure from the atmosphere pushing down on the ocean. So that is definitely playing a role in this 2009-2010 event, as well as changes in the ocean circulation. So there's lots of work on this problem. The paper from Goddard et al. Came out of Nature Communications. That's where most of what I showed you today is presented. There is north-south an onshore-offshore shift in the Gulf Stream. Tal Azer is a big name in the field. He's down at Old Dominion. He used to be at Princeton. He's done a lot of work on this problem. Wind stress changes from Andres et al., inverse barometer, Piusch and Ponte, I'm sorry about the name, ocean warming, Saba, bottom pressure changes, the Lander et al. Paper, NAO influence on AMOC, Zhao et al., influence of AMOC on the NAO, Bryden et al. So there's lots of different pieces of work. So again, we saw a big event in 2009-2010. It's correlated quite well to RAPID. It's got some pattern analysis correlation, which you can correlate the AVISO record as well to RAPID, and it's very similarly shown in models. I didn't show any models that, but it's something that we've anticipated for many years now. So yeah, it's a big deal, and it's an intriguing problem. I have some points that I wanted to take home. I mentioned the need for high resolution, and it's still something that I really believe is a big payoff potentially for high resolution ocean models as part of our climate. We know we need high resolution for high resolution atmosphere to do better for tropical cyclones. But these coastal impacts from the ocean are a pretty big deal, and I think that it's important to acknowledge that getting our resolution up in our ocean models is really, really going to pay off a lot for fisheries and for coastal impacts of sea level as well. And so the sort of ongoing hope is that by enhancing our ability to predict the AMOC well and have a good representation of the currents along the east coast of the U.S., we might in turn be able to predict sea level along the coast of the U.S., at least on a decadal time scale. Now, these interannual fluctuations that happen in 2009-2010 seem to be, they're a different time scale as well, and it's the ability to have predicted that particular event. I think that's another scale of prediction that may be more at the seasonal to interannual time scale. But the trend that is working on is something that I think we might get a grip on if we can predict AMO/AMOC variability. And the sort of final take-home point is that there is some compelling, however, controversial studies that are suggesting that the AMOC is has been undergoing a reduction in strength in the last few decades. And if you look at your SST anomaly from 2015 in the last few years, you'll see a cold spot over the North Atlantic, whereas the rest of the planet, relative to sort of the earlier part of the century, the rest of the planet is just getting warmer and warmer, whereas the North Atlantic is not that much. And that's consistent with a slowing down of the AMOC. If the AMOC is indeed slowing down, and on fluctuations on top of the AMOC, you will see these sea level rise events occurring more and more along the east coast of the U.S., like we had in 2009, 2010. And although it's, maybe 10 or 15 centimeters averaged over a year or two, that doesn't maybe sound like much, but, of course, these anomalies on top of that are big, and especially with storms and such as well. So I think that should basically be the end of my talk. I'll be happy to take questions if there's any time for that. Otherwise, I'm happy to let the next speaker take on.
Okay, great.
Thank you.
Thanks so much. That was excellent. So I do want to see if there are any questions in the room or online. If you have a question, you can indicate it with the raise hand icon. Oh, okay, in the room, is there a question? No, you said.
Okay, hi Steve, this is Anarita. Very nice talk. I have a question. So you hinted at the various processes that could have contributed to this particular event. I'm wondering if you can elaborate on the potential predictability, the lead time that's associated, for example, to the AMOC. So let's say if you see a fluctuation in the AMOC, what would be the lead time that would, have to actually predict some kind of event, over the northeast coast?
Yeah, it's a question that I think needs more study. The correlation in time between the fluctuations in the east coast sea level and RAPID is pretty rapid. I mean, it's in the order of a month or 2 or 3. You know, the resolution in time gets a little more difficult to distinguish when you get to that shorter time scale. But it's surprisingly fast, and I don't, to be quite honest, I don't understand all the mechanisms. You'd think there'd be some wave process, and on the order of a month or so sounds like a relatively fast sort of wave process that would be transporting that signal if it is something that is local to rapid. But there's also subpolar gyre processes going on too, and some people think the AMOC can be thought of as a coherent structure that, you know, northward and southward they act in unison roughly in some level, and a lot of people are questioning that. Some very smart people are. There's thinking that it's disconnected latitudinally. So that gets to the heart of some of the understanding of what the AMOC is all about, and I think that it's still uncertain to know. But just based on statistics of what the OBS were showing, it was a fairly close in time correlation. Rapid happened, and then within a month or 2 or 3, you saw something going on in the Northeast along the tide gauges. By the way, I wanted to mention, thank you, Anna Rita, this was funded by a NOAA proposal with Yin and Griffiths and Zhang. So thanks to the NOAA people who supported this. It may be MAP, I'm not sure.
And Lucas in the room, she's here in the room. Smiling, so.
Yeah.
Hi, Steve, this is Andy. Thanks for the shout out. I appreciate that. And great job on
yeah, sure. Sure.
Okay, well, great. Thanks so much again for the presentation, and now I'll transfer over to Elaine. Elaine, are you there?
Yes, I am. Can you hear me?
I can hear you, and you should be able to share your screen. Let me just introduce you. So Elaine Miles is joining us very early in the morning in Australia. She works with the Australian Bureau of Meteorology, and she's a physicist by training, and Elaine has worked in a variety of areas, including art conservation, which is really interesting, as well as numerical weather prediction, data assimilation, rainfall forecast verification, and prediction of seasonal sea level anomalies. And her current role is within the Climate Information Services branch, where she's working to deliver historical ocean data to the public. So Elaine, take it away whenever you're ready.
Thanks. Before I begin my talk, I just want to acknowledge the help of fellow researchers, Claire Spillman, John Church, and Peter McIntosh, in completing all this work over the past couple of years. What I want to discuss today is the prediction of seasonal sea level anomalies within the Bureau of Meteorology. And basically, by the end of this talk, I would like to have 3 questions answered for you, which is, why should you care about seasonal sea levels? How good are the Bureau of Meteorology seasonal predictions of sea level anomalies, and why does this occur? And how can you access the seasonal predictions of sea level anomalies through the Bureau of Meteorology? And if you're interested in any of the content of this talk, it's mostly based on 2 papers that we've released in the past 2 years in Climate Dynamics and GRL. So, as many of you are already aware, and from the past 2 talks we've just seen, sea level extremes are a combination of events, one of the big ones being climate change. And around the Western Pacific, this signal is very strong. So here I've got a plot of the sea level projections for the Solomon Islands, where we can see that by about the 2100 we're seeing rises of, upwards of 50 centimetres using the SRES A1B projections. But additional to that, we also have other factors playing on top of seasonal variability, regional variability, and weather and tides. And unfortunately for a lot of the nations in the Western Pacific, when these factors hit their maximum and coincide together, this can lead to some very devastating effects such as coastal flooding and inundation and storm surge. So if you have a look at current products that are available around the world and also at the Bureau of Meteorology, there's a lot of products relating to sea level rise, which acts on, the scale of hundreds of years, mesoscale eddies, storms, tides and waves, which operate on the more 2 hours to 2 weeks time frame. But there's a big gap around here in the seasonal to intraseasonal period. And that actually plays a big can play a big factor in these inundation events, where you've got El Nino factoring into the sea level extremes, seasonal events, and the Madden-Julian oscillation. But there doesn't seem to be actually a lot of seasonal prediction of these events. And so what we sought out to do is to see if we can use our seasonal prediction model at the Bureau of Meteorology to predict these phenomena. So just to provide a little bit of background, this project was part of a AusAid funded project called the Pacific Australia Climate Change Science and Adaptation Planning Program. And this was the Seasonal Prediction of Sea Level Anomalies project. This project was brought about because there was recognition that climate change impacts will be very significant to Pacific nations, and there was a limited amount of knowledge available to these nations. And so we wanted to create a stronger science background for understanding the seasonal sea level variability and predictability within these regions. And by doing that, report on the skill of being able to predict seasonal sea level anomalies in this region, and develop for the users at the National Met Services experimental seasonal sea level forecasts for them. And the outcome being that we'd like to see better coastal zone management to enhance their resilience under climate change, and also just to improve community and stakeholder awareness of how climate influences the climate zone. And just to give you a scope of the spatial scale that we were looking at, we're mostly looking in the Western Pacific, and we worked with 15 partner countries to create these forecasts and to disseminate the information. So, really quick overview of the model that we used. It's the Predictive Ocean Atmosphere Model for Australia, also known as POEMA. It's used operationally at the Bureau for Australia to predict rainfall and temperature for the upcoming season. And it's a dynamical coupled model where we have an atmospheric model that is also takes in atmosphere and land initial conditions, which is coupled to the ocean model. Sorry, I'm a little bit hazy because it's so early in the morning. It's coupled to an ocean model that spans the globe. Just to emphasize a few key points, the ocean model is the GFDL MOM2 system, and it's been configured for a 2-degree zonal and a 0.5 to 1.5 degree resolution from the equator to the poles, and it consists of 25 vertical levels with a maximum depth at 5K. The ocean initial conditions is run by a system called PODAS, and that simulates in-situ temperature and salinity observations from CTT, XBT, the Tau, Trident, Parata, Array, Reynolds, and Argo. There is no satellite observations going into it. And this model is run in what we call multi-model mode. So there's 3 different model configurations, each with 11 ensemble members, which means when we produce the forecast, we actually have an ensemble of 33 members, and from that we can create probabilistic forecasts for our users. So the method that we used in these papers was to evaluate the skill of POEMA, which, as I'd like to emphasize, is a dynamical coupled multi-model ensemble seasonal prediction system to model seasonal sea level anomalies. This is the first of its kind in the literature. There's been quite a few papers in the past which were looking at statistical models. So this is a step up in the forecast systems. We used POEMA hindcasts, which ranged from 1981 to 2010. We investigated it using CSIRO's altimeter record, which had the glacial isostatic adjustment, global trend, and inverted barometer factors removed. And we also looked at tide gauges, which was available, the available period being site dependent. Just a few notes on sea level anomalies from POEMA. There is no data assimilation of sea level, so it's independent of the tide gauges and the altimeter measurements. But one slight drawback is that it's a rigid lid model, meaning the volume is conserved. And so we don't see any global trend, glacial isostatic adjustment, or effects from atmospheric pressure. Also, due to the general size of the grid cells, you don't see effects such as mesoscale eddies, and also the effects of tides do not come into this model. So there are some limitations to what the model is forecasting, but it still provides some very useful information. So if we have a look at the model skill targeting summer and winter, so summer in Australia being December, January, February, and winter being June, July, August, Arun's already described persistence forecasts, but what we've done is we've assessed the skill of Poema against altimetry data. So on the left-hand columns of each of the two seasons, we have persistence forecasts, which is where we've taken the altimeter data set and gone, what's the forecast for tomorrow? It's today's forecast. What's the forecast for the next few weeks? It's what's happening today. And that's like your poor man's forecast system. When we have a look at how the model predicts the December, January, February, and June, July, August seasons 1 month in advance, we can see that persistence forecast actually performs relatively well in the Western Pacific, and there seems to be a change in December, January, February, persistence performs better in the Northern Hemisphere, whereas June, July, August we see higher skill in the south of the equator. But if we look at Poema forecast, we can see an immediate jump up in skill over the whole domain. If we look to 6 months in advance, so this is the instance where we're using a forecast that is initialized in June to predict December, January, February, persistence forecast skill drops right off for both summer and winter, whereas Poema still maintains some relatively useful skill in the region. The June, July, August season does tend to be a lot weaker than what forecasts for December, January, February, and that's because Poema does suffer the effects of the spring barrier prediction, which is where it's very difficult to predict what the next upcoming ENSO is when you're starting from December, because that's when a lot of change can occur with the wind fields. And so just to highlight that a lot of the skill of Poema predicting sea level anomalies comes from ENSO events, is that we had a look at composite ENSO events for both altimeter and Poema. So the top row shows altimeter composite events, so the left-hand side showing El Nino and the right-hand side showing La Nina for the 5 strongest events using the NINO 3-4 index. And what we can see in the altimeter records is that when we have an ENSO event, we have this very strong dipole feature in the Pacific where El Nino sees lower than normal sea level anomalies in the Western Pacific and higher out in the east. But interestingly, we also see this strong monopole feature in the Indian Ocean for both the El Nino and La Nina systems. And that can be seen as part of the, typically when you have a strong ENSO event, it's normally followed on with a strong IOD as it moves through the Indonesian flow-through. If we turn our attention to Poema's forecast, where we've got a lead 0, a lead of 3 months, and a lead of 6 months for these strong events, we can see that Poema does a pretty good job of capturing the general shape of these events for both El Nino and La Nina, although it does appear that the cold tongue extrusion does come out a little bit too far west, which can have a strong impact for locations that are near the edges, near the date line. And also, it's apparent that Poema does not quite capture the strength of the El Nino events, typically being a few centimetres lower than what's actually seen through the observations. And as you'd expect, the further out with the lead time you go, the less representative of the observations the forecasts are. And that's because POAMA tends to drift towards a climatology state the further out the lead time is. And just for a little bit more of a technical analysis, if we have a look at the variability modes of the altimeter and POAMA for December, January, February, and June, July, August, we can see where altimeter is in the center column and the POAMA forecast within on the right-hand side. We can see that, and this is for a lead time of 0 months, we can see that altimeter and POAMA, in terms of like the amount of variability described by the first mode, they compare relatively well, altimeter being a little bit stronger than POAMA for both December, January, February, and June, July, August. But if we have a look at the principal components in terms of like, do they track well over time, they have very high correlation skills. So that shows that a lot of the skill of POAMA is actually coming in through this major mode of variability from El Nino in the Pacific. And that's all very good and well to look at the open ocean over the whole entire Pacific, but a lot of our users are actually, they're located on coastal islands, and they would actually like to know how accurate the model is relative to their tide gauges. So as part of our study, we investigated 20 tide gauges throughout the Pacific and even snuck in a couple around the Australian west coast to see how well POAMA, if you take the nearest POAMA grid cell relative to a tide gauge, how well can you predict the seasonal sea level anomalies at those sites. And it turns out you can do a relatively good job. So what we have in these two figures is a lead time of 0 months and a lead time of 6 months. And we're looking at a tide gauge in Malacca, which is a little bit more towards the east Pacific near the dateline. And sorry, I've got that around the right. The Western Pacific is Malacca, and Christmas Island and Kiribati, which is a bit further out towards the Eastern Pacific. And what we can see where the solid line is the observed at the tide gauge, and the dashed line represents the POAMA forecast at the nearest grid cell, is that at the 0 month we are seeing that the forecast and the observations track very well with each other. If we move out to the 6 month forecast, where the solid line is showing the observations, the dashed lines tend to follow along relatively well in terms of the general shape of the forecast in capturing the major events, but we do see a little bit of model drift occurring. And if we actually have a comparison of all of our 20 sites, 20 tide gauges over the record, where blue represents the POAMA forecast skill measured by correlation, and red represents a persistence forecast using the tide gauge observation from the start. We can see that, and where these figures are being arranged in, so we have Australia, Western Pacific, Eastern Pacific, and even a few sites in America, we can see that POAMA consistently beats out the persistence forecasts for all sites, although we do lose a lot of skill when we hit up over to the East Coast, to the Eastern Pacific as well. And that's mostly because a lot of these nations, a lot of the tide gauges are located in sheltered areas, and they can just see the seasonal signal come through at a nice, smooth motion, whereas Poema does struggle getting some of the coastal current conditions along the west coast of America and the west coast of Australia. So we've developed web pages to develop these forecasts, to deliver these forecasts to our users. We have an online portal, the website of which you can go check out down here at this link here. We developed quite a few products showing sea height anomalies, probabilities, small indexes for each of the countries, and as well as that we've provided skills for all of the forecasts so that people can investigate if they've got a forecast coming up, just how accurate should it be coming in the future. So in summary, extreme sea level events are a combination of global trends, seasonal events and weather events, and Poema shows good skill against tide gauge stations and altimeter observations, feeding persistence for predicting the seasonal component of these events. It's able to capture the phase variability in physical processes in the Western Pacific. I didn't show it, but if you have a look at the papers, there is skill there are skill plots for the Atlantic, but they are certainly nothing to boast about. But we are able to actually, in the Western Pacific, provide forecasts of sea level anomalies with high skill out to 7 months in the Western Pacific. This is very exciting work at the time because it was the first experimental dynamical seasonal prediction of sea level anomalies in the world. There has started to be some more work I've seen with the CSF, and as well as that creating multi-model ensembles with partners in Hawaii and NOAA. So it's an interesting space to watch. As well as that, we have an online portal available for any user to drop through and investigate. So thank you for paying attention to my talk, and I'd just like to acknowledge Australian AusAid, Bureau of Meteorology, the Australian Department of Climate Change and Energy Efficiency, and CSIRO for funding this work.
Elaine, thanks so much. That was great. Are there any questions in the room for Elaine? One online? You can indicate, you can virtually raise your hand and let me know you have a question and I can unmute you. Okay, well if not, Elaine, thanks so much for joining, especially at such an early hour.
No problem. I'll have to find a cafe soon with coffee, I think.
Sounds good. Okay, so now I will introduce our last speaker, and hopefully I can figure this out, or I actually need to bring it up on our computer here because he's in the room, Billy Sweet. And I actually need to control. I can actually see if I can. I don't think, yeah, I can't. Let's see. So I don't think anyone can see it yet. Oh yeah, okay. Your screen. All right. So I'm loading this. Okay, so Billy Sweet is an oceanographer with NOAA's Center for Operational Oceanographic Products and Services, co-op. He's focused on detecting and explaining sea level extreme trends and patterns that are important for resiliency efforts. His work is helping NOAA and other government agencies develop coastal planning guidance for an uncertain future. He received his PhD in oceanography from NC State and his undergraduate in physics from the University of North Carolina at Chapel Hill.
Great, well, thank you. So today I'll talk more in sort of statistical model frame and pick up on some of the basic underlying discussion that we've had in terms of changes in the mean, but in this case I'll strictly focus on actual impacts that are experienced along the coast, measured by tide gauges. Ultimately, that's what's impacting. The mean oftentimes drives these changes of extremes in time, but it's the storms and tides that people notice and are concerned about with rising sea levels. So in this case, for current tidal flooding, otherwise known as nuisance flooding or sunny day flooding, it includes anything above some sort of set threshold, so it could be the most, the rarest of events, the hurricanes, direct landfalls, but in terms of the distributions, they're much more infrequent compared to the more frequent lesser extremes. So for the most part, they're really looking, they're dominated, weighted by the lesser extremes over some threshold, and we'll talk about that. These are becoming problematic, damaging people's cars as you drive through salt water, degrading stormwater infrastructure, roadways, transportation, impacting communities and livelihoods more so than in decades past. So a little bit of that. The idea of the seasonal predictions or annual predictions is important so people can municipalities plan correctly in terms of having budgeted for temporary pumps, sandbags, private owners, water getting into pools, downtown stormwater pump systems, future upgrades, let's say. So many reasons to understand your current situation and what to expect. We know that this sort of the storm tidal flooding follows regional seasonality. So here we'll focus a little bit on the intra-annual variability. As discussed, sea level rise is actually causing rapid growth in these annual flood frequencies, and it's actually further compounded on an interannual basis by El Nino, is what we've seen in some of the earlier talks. So setting the stage for sort of my approach, first we need to define some high tide thresholds based on tide gauges that actually equate to some local impacts. Identify some seasonal and regional patterns in physical forcing and high water climatology so that we can take that leap from the annual down to the seasonal, which I don't do, but I will show patterns and make sense of it. Sort of establish some contemporary baselines from that recognize sea level rise, and I think baseline is important whether or not you're talking datums or the period of record as to which you're establishing climatologies to make assessments. We'll quantify this sort of interannual El Nino Southern Oscillation, or ENSO's, effects through a bivariate statistical model. And lastly, based upon sort of an empirical type projection of tidal flood frequencies, using some guidance sort of in a hybrid sense of these multi-model ensemble predictions of what the actual ENSO or the Oceanic Nino Index strength will actually be to guide sort of the historical statistical model. So around the country, we start to experience, in the U.S., we experience minor impacts about 1 to 2 feet above sort of this highest tide level, the mean high water datum, but typically sort of what people tend to build by. So a foot or two above, we're vulnerable. We know this from tide gauges and efforts from the local weather forecast offices and emergency management that through years of impact monitoring have noticed that at certain levels, certain impacts will occur. So again, we're sort of assessing the whole distribution of water levels here and focusing on a certain percentile or certain threshold of minor impacts, or otherwise known as nuisance impacts. So really you look at a time series of your tide gauge and you might have these various impact levels determined at a particular site, and we'll make counts of days, and you can also do total hours in a year, and I'll use a meteorological year here, May through April, so not to split the winter season, and we'll keep these counts. So in New York City, for instance, if you exceed these levels, these citizen science efforts that capture pictures, and you can see that flooding happens in neighborhoods, water gets onto roads, retaining walls of major, railroads are becoming compromised. So it's a bit more a nuisance, let's say. So looking at the seasonality around this, and I think this leads to a certain understanding of seasonally when do the impacts actually manifest. We know New England, we look at the wintertime, that's generally a nor'easter exposure. You have more winter storms. Whereas it's more dominated in the southeast and to an extent from the mid-Atlantic, and the Gulf is more of a fall cycle, and that's really going to be controlled by the seasonal cycle and mean sea level, more so than your frequencies of storms themselves. In the south, people live there, it's a lot calmer, you don't get these storms as much, why people move there from the northeast to the southeast. The West Coast, it's winter. It's really controlled by your spring tide cycle, and as it nears the solstices, you get a strengthening of certain constituents. So we can actually start looking at the seasonality of exceedances of these in a distribution sense. And here's an example, for instance, at San Francisco, the black top line would be based upon 30 years, looking at your highest calendar day of event, smoothed by a 30-day running mean. Sort of gives you a feel for when your high water events, the components of them then. So the solid blue line would be the tide cycle without any seasonal cycle to it. The dashed blue line would be the seasonal cycle. The green would be this non-tidal residual, oftentimes called a storm surge, but it's anything that's not deterministic from the tide. The yellow and pink, magenta dotted line are these local thresholds. The black dotted line is this high tide threshold, mean high water. A lot of information here. Underneath each one of them is exceedances by sort of calendar month, and sort of the take-home message that reinforces what we just saw is that, let's say in San Francisco, you tend to have your exceedances sort of clumped around your solstices, more so in your winter solstice, which is also exacerbated by your winter storms that do occur. Whereas, let's say the Battery in New York City, it's much more of a sort of a nor'easter, a non-tidal. The green line is really sort of the one that's dominating. Whereas in the sort of the Mayport, Florida, and Port Isabel, you really see this real pronounced peak in the mean sea level cycle, the blue dotted dashed line that you have upwards of a foot difference in mean sea level, let's say in September, October, and November timeframe than you do, let's say, in the late winter. And that's due to seasonal changes, but the tides are riding on top of that, so they tend to be more impacting. So if I take an average, let's say, of the black line observed compared to the sort of the green, the non-tidal, and I do a ratio. Mark Merrifield did a similar ratio in a global sense, but here we do it for the United States, and we look at those that are bluer tend to really be dominated by the tide. The non-tidal residual is much less of a factor. It's really determined more so by the tide, whereas the red is much more non-tidally dominated. So you see, let's say, the orange and red tend to be in the Chesapeake and the Gulf. Small tidal cycles, a lot of noise from atmospheric forcing. Whereas your blue, you really have large tide ranges that really dominate when these things happen. So, for instance, your king tide watch, they really do tend to happen right around these predicted high tides, more so than where you'd be atmospherically sort of dependent. And so an example, let's say Miami, here's the predicted tide, and we actually see what the actual observations, this was the last 2 years ago when everyone, the White House was getting excited too. They were going to fly around and take pictures of high tide flooding. A colleague of mine goes by Obey, took a picture, he's in the airplane with a helicopter with a senator, and they found some high tide flooding on the day that the high tide flooding was most likely to occur. The same sort of highest tide of the year type event in the Chesapeake happened about 5 days before the highest predicted tide. It was a weather event. So it just goes to show, it depends on where you are as to when these things will actually manifest. And here's an example of the type of signage you will see. All right, so the seasonality, now let's talk about the long-term changes. As we've heard, relative sea level is what's really driving a lot of this if we want to look at changes in time, and it's land subsidence as well. And so this sort of change in baseline is important as we keep track of frequency changes of exceedance. Here's a change, long-term changes in relative mean sea level, high subsidence in the Gulf area, relatively high rates all along the mid-Atlantic. The tides really are changing, so if we look at the 5-year daily maxima relative to a local threshold here in Norfolk, for instance, you do have storms that come in, but you really just have much more of these events are becoming rather common due to the fact that local sea level rise. And so I think that goes into establishing some baseline. It's important because at the end of the day, communities are going to want to sort of have a contemporary assessment of the number of exceedances they might expect, more so than normal, let's say, and the normal being a non-stationary trend at this point. So this would be, again, these are daily maxima. They're not just a whole tidal cycle. So really the shift in distribution, if I look at daily maxima here in an empirical fit, it's just a probability density over a 50-year span. You know, sea level rise really has shifted, and relative to a nuisance level, let's say, you know, you have your historical years, days per year with an exceedance, and in the background's a church in Norfolk with a high tide calendar posted because they get so much flooding you're going to drive through water to go to church. But it's really characterized by a quadratic fit now. So even with more or less linear sea level rise, because it's nonlinear area under the curve type distribution as it shifts, we're getting clear acceleration in the number of days per year with impact. And that's really sort of the case going around the country. Maybe less so either where your threshold's too high, you're still in your pretty, you know, extreme distribution itself, you're not getting enough exceedances, or if sea levels in general has been more punctuated, let's say during El Nino, the West Coast, you tend to get a lot of sea level, decades of sea level in a year, whereas your last 20 years or so, it's been not nearly as clear of a signal, so maybe you get more of a linear response. But looking at sort of this annual or seasonal predictability, let's say, or consequences of El Nino, in this case we'll focus on El Nino. We know that you tend to, we've seen from other talks where you get your heat and deeper thermoclines, higher sea surfaces for months at a time, a lot of persistence as we've seen and heard. So when we actually look at mean sea level here, monthly mean sea level of San Francisco, you have a pretty tight correlation as we've seen in some of the other talks. So more storms and more your typical storms and tides are riding on a higher sea level and become more impacting. Whereas in your East Coast, we're getting more of this atmospheric response that we tend to get more northerly wind forcing. We saw a case in the 2009-2010 that Stephen had talked about, but that's also typical during other stronger El Ninos. You get more either surges or you get these quiet anomalies. Maybe there's not really a storm in your face, but it's the conditions offshore that are Ekman-type response. So when we make these days where your non-tidal residuals of foot or higher, they really start to line up during these El Ninos, the stronger El Ninos in particular. And here I'll point out sort of some stronger El Ninos in the red, more neutral conditions in the gray, and the blue being stronger La Nina. And we'll really see what this does to the interannual signal at some locations. So here I detrend the daily maxima because I really want to sort of highlight variability not associated with the change in sea level. And you can see in this case in San Francisco, you tend to also have a change in the mean and a variance. And here I fit with a normal distribution. Here it's daily maxima. They're not really normal. They're more normal. You could do the whole fitting exercise to figure out exactly what's best, but a two-parameter sort of parametric fit here in terms of the maximum likelihood, it's actually significance in the mean and the variance. And again, to point out, La Nina has sort of the opposite here. When you go to the East Coast, you definitely see a shift in the stronger El Nino, and this is the composite of those strong El Ninos, so this is the more extreme case. But the neutral and the La Nina don't really have any signature. It's more so the stronger El Nino tend to really cause these types of changes, both in mean and variance. So you tend to have these prolonged sort of background set up in sea level, but you also are more punctuated by more storms. Your variance is increasing. And so overall with that, then if I use, if I look at the historical count here, and this would be extracting the data that was in that 3D colorful plot here, looking at two stations, number of days per year with an exceedance, I can fit with a trend or a linear trend or statistically what's significant here. And, you know, the R-squareds aren't too bad. I don't show them here in Norfolk. It's about R-squared of about 0.45, and San Francisco, not too good, 0.15. But when I also in a bivariate sense use an annual value of O and I, the significance of the fits really increase. And so from that too, then I can use what I had mentioned before in this hybrid fashion, based observations as well as up to I think the first few months of the year, this meteorological year, and then the multi-model ensemble plume average that is put out through IRR and CPC and others. So then I can start to make this annual sort of projection of what we would experience based upon sort of this bivariate model. and then I can start quantifying what it might be relative to sort of the change in baseline associated with local relative sea level rise and the response that we historically have evaluated. So then we can start making sort of percent increases that we might expect over the coming year. And we put this out last summer to say, you know, heads up, a strong El Nino is occurring based on some earlier work. We can start to deliver maybe some useful information. It listed where there's significance with El Nino. If there's no call out in parentheses, then there was no significant over the 90% level here in terms of the bivariate nature of it. So when we actually then assess relative to our prediction the number of days in this year up to basically February 29th leap year, we have 2 more months left to account here. We've already broken records where the red stars or broken records, the red dots would be above what's already been predicted with this bivariate sense. The blue would be we haven't broken the El Nino-based prediction yet, though at most of these areas we're very close, and I would imagine we are. The black stars, we broke all-time records, though there was no ENSO sensitivity historically characterized. So in conclusion here, you know, getting this to a seasonal scale, I guess, is the ultimate sort of goal, is to give people sort of the next few months and sort of characterize. So I think in this case, sort of need to look at sort of fitting distributions, whether they're parametric or non-parametric, of these daily maxima seasonal tides, and maybe do some assessments, significance of how do they change under various ENSO phases. Look at using some of the dynamical model output that we've heard a few talks on discussing, and themes of seasonal guidance possibly and changes as the mean to shift the distribution. Yet we need some sort of distribution though to shift. And that's also important because we may not have sort of historical ENSO sensitivity that the dynamical models, though they may not be as strong in some of these areas that historically don't show up with the strength of ENSO, but that would give us some guidance. And here, a quick call out, I think Lane's model is actually represented in here, this Pacific work, the International Water Level Service that John Mara, a colleague of mine, who I should have made reference right off the back in the talk, he and I have been working together and brainstorming a lot of this. Just an example of many different ways, statistical and dynamical, to start providing some guidance, 6-month type guidance of a sea level anomaly that then might be able to use to basically assess or give guidance, let's say, of high tide events that folks might use in terms of actionable information. Lastly, we need to deliver this in terms of projections above flood frequency, and I think it's important when we do this to show how the baseline is changing and maybe relative to some longer-term projections, so folks can get a sense of, you know, what's coming this next season, next year possibly, and how does that assess to some longer-term potential changes. And here we did this in some work where we show what's happened, and then we start fitting here. I use Bob Kopp's local sea level rise projections to change some empirical distributions under the sort of the concentration pathway initialization of the models, and so you can start to see, you know, where you stand relative to a possible future. So not only are we given seasonal guidance, but we can possibly put that in context of some longer-term changes for getting from the preparedness to maybe the more planning realm side of things. So with that, I'll close. Thank you.
Great. Thanks so much, Billy. Does anyone have questions in the room?
Yeah, I guess I'm just curious whether you have applied this technique, or this empirical technique, like in a handcast mode.
I have. Well, I guess the bivariate model itself provides, you know, a significance level of past assessment, though I have not necessarily. I've used the distributions and I've split them back ways and compared to observed levels to assess sort of like a root mean squared error. If you would assume a typical distribution, how might that assess to historically if you start making these projections, knowing that you're assuming sort of a smooth change in sea level, whereas we know there's variability. I think, again, sort of in the statistical sense, knowing sort of the standard error of the regression, the bivariate regression itself gives you some assessment, though. I think there's probably still work to be done in terms of assessing the overall skill of a sort of a statistical model and how might it best benefit from, you know, refinement.
Hey, are there any questions online or from any of the other speakers, Arun, Elaine, and Stephen?
I had my hand up.
Oh, yep, yep, I see that, Arun. Go ahead.
Thanks for the talk, William. Do you have any physical basis of anticipating that the variance would change, or any reason for thinking that it should happen that way?
On the East Coast or West Coast, or either?
No, anywhere.
Well, I think what's being picked up on the variance is some of the work we did in the paper was basically looking at storm. There have been some atmospheric studies done looking at storm tracks tend to track more along the East Coast during stronger El Nino. So that's sort of what a 2011 study we looked at from a storm surge response. Phil Thompson, University of Hawaii, has also looked at that in terms of modes of ENSO, looking at basically cyclogenesis coming out of Gulf of Mexico and tracking up the East Coast. So there is, I think, some sense in terms of storm track changes during that. In the West Coast, I guess there is some additional storm track changes as well, but I think the variance tends to show up more so on the East Coast right now. And we do have some ongoing work looking more at extremes, not the lesser extremes, with some time varying sense with Melissa Menendez and others that are starting to show some sensitivity in the more extreme events, not necessarily these sort of lesser extreme or common day events as well. That's starting to pick up some of this change as well. So definitely needs to be looked at too, and your models might actually help show that.
Thanks, Arun. Are there any other last questions? Hey, if not, I want to thank again for our four speakers for really excellent talks, and thanks for joining. And our webinar is coming up in April, so hope to see you then.
Thank you.